with Reinhard talking about census and scaling relations of outflows in star-forming disks.
All right, so we are back to the real universe, and I'd like to show you the results of a fairly major sub-program of our KMOS 3D effort, led by Natasha Förster-Schreiber. In fact, you will find this the results of what I'm going to talk about in this AstroPH led by Natasha. So basically, can be short on the motivation. We've seen this diagram before, abundance matching and the inefficiency of galaxy formation on either side of the famous peak, and the idea that this is due to supernovae, the second most important item in astronomy, and perhaps so the assumption is on this side, galactic nuclei, black hole accretion might also help in making galaxy evolution inefficient. So the question is, how can we test for this? And the route we've chosen is to basically take the fantastic capabilities of KMOS, the KMOS spectrograph. KMOS is a multi-IFU spectrograph, so you can have up to 24 integral field units located in a 7 arc-minute patrol field and observed simultaneously. And our choice from the initial get-go in 5 years ago was to basically pick one band, K-band and H-band, one redshift, 3 redshift slices, 0.7 to 0.9, 1.5, and then 2 to 2.5, and go deep. So we've not done what Mostef did to basically try to get a full coverage in band, but instead get very, very good spectra. So that has helped now for this program very much, because we have been able to extract from this sample, which is about 700 plus galaxies, a subsample of 600 galaxies. Now, some of them, in fact, were part of the SIN survey already, but the dominant part of the 600 are KMOS 3D sample. These are galaxies drawn from the Candles 3D HST parent sample. And in fact, if you look down here, normalized to the main sequence now being horizontal in both of these plots, in star formation main sequence offset versus stellar mass, and size versus stellar mass. The parent sample down here is in gray, and this is the KMOS 3D SINS outflow sample, which we've drawn from this in the different redshift slices as I described. So typically, the typical median integration time is 8 hours per object. And so the dense coverage, very much like what Kevin told us for his work, where we've basically sampled the main sequence plane here in approximately the same densities throughout, thereby getting good statistics at all locations. And so we were able, in fact, then to pixelate, if you like, pixelate the plane, certainly on the main sequence, but you see we even have galaxies below the main sequence and a little bit above the main sequence, and get average properties of these galaxies. And so the way we deal with the galaxies for this project here is we first go ahead and subtract, remove any ordered motion, because we don't want to be fooled by the rotation of the galaxy. So we remove the ordered motions and then look at the inner parts, typically, of the galaxies. These are seeing limited data, so the inner parts of the galaxies, and extract a single spectrum. So then we have, for each of these 600 galaxies, a single spectrum typical for the inner parts of the galaxy. And then in these spectra, which are K-band spectra, for redshift 2 would be K-band spectra, covering H-alpha, Nigen 2, and sulfur 2, you can then look for broad components. So that's basically the idea. And so If you ask, then the first simple question is, where do we see, in which of these objects do we see outflows? Then you can see sort of plotted in the same way that we see many outflowing galaxies at high mass, both above and below the main sequence. In fact, into the red sequence and green valley. I mean, so we see them everywhere. And so if you plot the incidence in this pixelated scheme where you pick the size of the pixel to have 10 galaxies each, same density, then you can color code this in some fashion. You can see that, in fact, as you go from this side of the main sequence to that side of the main sequence, the incidence of outflows increases. That's one way of looking at this. There's a very nice, smoother way of doing this through the so-called LIST technique invented by Capillari, where you do a local smoothing of the densities of the incidences you found, and that basically just, makes the appearance of this pixelated picture a little nicer and easier to read. So that's the first step in terms of the data. The next step, we already knew at the time when we were starting this, that there were two different types of outflows. One, what you might want to call stellar star formation driven outflows with moderate velocities. And then the second type, which we discovered in those data, and other people have seen it since, basically characterized by very high velocities and in AGN-like profiles, which you might want to call AGN-driven outflows. So here is a stacked spectrum of about 30 of these star-forming outflows, and you can see clearly the characteristic of the star-forming gas, the narrow gas. But then if you look at the pedestals down here, you clearly see a broad component occurring in all of the lines. So it's not just H-alpha, it's nitrogen 2, it's also, in fact, the sulfur 2. That's a very important piece of progress, which we had been hoping for, is in that this has now given us, for the first time, a direct measure of the density, the volumetric electron density in the outflowing gas. You will see what that has helped us to do. So this type of outflow, you would say, is a stellar-driven outflow if there is no known X-ray AGN, if the narrow N2 over H-alpha is star formation like in the BPT diagram, and that is typically then a outflow velocity of about 400 kilometers per second. And the N2 H-alpha in the broad component, empirically what you find here, actually matches very much what you see in the narrow component. So it's photoionized gas. The second type of outflow obviously looks very, very different. That occurs either in X-ray AGNs or when the narrow N2 over H-alpha is liner-like. So in this case, obviously, you see that the narrow H-alpha and nitrogen 2 H-alpha line is high, greater than about 0.5, then you would call that a liner. In those cases, you see a very broad emission, also in sulfur 2, in fact, dominated by N2 in most cases. So the N2 over H-alpha broad component on average is on the order of 1 or greater. So it's, again, liner-like. The outflow velocities are much greater than here, typically 1 to 2,000 kilometers per second. This we call AGN feedback. Now, mind you that the number of quasars in this combined fields we're working on is relatively modest, maybe 5 or 6. So we're talking about AGNs which are reaching from 10 to the 45 ergs per second, very rarely, but mostly into 10 to the minus 3 to 10 to the minus 4 Eddington, which you would call Seyfert-like. Okay, so in fact, this is very important that we are reaching beyond what people usually look for. In fact, I would go one step further. You find in the literature a lot of work basically taking spectra on AGNs. Okay, I would argue that's not the way if you want to look at the role of AGNs in galaxy formation. You want to look at the parent sample and then check out, so to speak, what the properties are, independent of whether the AGN in there is on Fridays, so to speak. You also want to look Mondays. And in fact, that's a very important part. The fraction of what we call AGN, only about half of those are actually X-ray AGN. So had we only picked on the X-ray AGN, we would have underestimated the fraction of objects which have AGN-driven outflows. Now, you want to, of course, know that what you're looking down here is not a broadline region, okay? And that can be seen, as I said, if you see a broad sulfur-2 emission, also on the symmetry of the combo of these three lines. In fact, I should comment, if you go back to the famous Hohn-Filipenko survey in the 90s on nearby AGN, you will find quite a number of these objects, and you can identify the outflowing galaxies by the centroid of the broad component being redshifted. This is due to the strong nitrogen 2-line pulling, essentially, on the overall profile. Okay, so this is the kind of analysis which we can do, and we can now separate the emissions. We don't, of course, spatially resolve in this full survey every one of these cases, but we do have galaxies where we do. Here's one galaxy with a PV diagram where you can see both types of outflows in one galaxy. So the rotation of the galaxy, in fact, is this and this. It's hard to see down here, it's extincted. But then you see this broad smear here. That's the stellar outflow in this case, clearly resolved spatially on the scale of the disk, and we've seen that in other such cases. But even the AGN outflow, which is this here, is also resolved, just about 1 to 3 kiloparsec. How we fit the blue and orange line. So for all the lines, we always make the assumption that all species, all lines have the same width and the same velocity. Okay? And so we are fitting for the width of one of the components, which is the broad component. Well, you fit at the same time. You do an MCMC type fitting. Okay, now let's start with the stellar feedback. So we've now separated the sample in what we think are star-forming dominated objects and AGN-dominated objects. And now we are looking at the incidence, and we also at the same time we can look at the strength, same thing, of the outflow in star formation outflow galaxies. And here's the Luss plot of the incidence. So that's the stellar mass star formation rate plane again. First of all, I don't show you any redshifts anymore because redshift is not a coordinate. If you do a formal PCA analysis, redshift does not occur as a component. So it looks the same at all redshifts. So we can average. You see that basically the incidence only knows about up and down. So you see fairly prominently a third or up to a third of all galaxies above the main sequence into the outlier sequence having outflows, but if you go below, you don't. Nothing about mass, nothing about size. So I could show you a lot of other plots which are all dead boring. Now, what we do know is that another way of plotting is as a function of star formation surface density. So here's log m again, and here's star formation surface density. And the same thing. High star formation surface density galaxies have outflows. In fact, there is a clear breakout kind of a situation where above a certain star formation surface density of about 1 to a few solar masses per year per kiloparsec, you see winds, and below you don't. And you can understand this with the same kind of semi-analytics we saw earlier today, where you basically look at the momentum driven by star formation rate and look at the balance of the gravity of the overlying layer against that push, and ask the question, when do you have an outflow? And then basically you come for the kind of gas fractions we're talking about at high redshift at a breakout at around 1 solar mass per year per kiloparsec. Now, you would expect that the outflow rates depend on the electron density and other parameters in this fashion, and thereby, if you go through this, and depending on whether it's the momentum or energy driven, the mass loading factor should depend on stellar mass, either like -1/3 to 2/3. That's the expectation. And that would expect you to, for the small galaxies, to have high mass loading, and for the higher, you don't. Now, what do we find? Well, actually, we find a result in mass loading, which is somewhat falling, but significantly shallow, I would say, or even flat. Moreover, we find that the outflow velocity is only typically 1.5 to 1.8 times the circular velocity. So that means these winds will not get out of the galaxy much. So these star formation-driven winds we are seeing will trigger, most likely and certainly at the highest masses, fountains, but not drive galaxy out into the outer halo. The derived mass loading factors are low. That's a surprise to us. And that's because the sulfur-2 ratio tells us now that we have actually fairly high densities in the outflowing material, much significantly larger than in the narrow component, the star-forming gas. So we're looking at, like in M82, we're looking at entrained dense filaments in these winds rather than the total wind fluid. So the typical mass loading you find is about 0.2 to 0.3 rather than 1. Now let's go to the AGNs. So again, the same plot here of incidence as a function of stellar mass and star formation rate. Now, as you see, the AGNs don't know anything about up and down. They only know about left and right. Well, okay, a little bit. I barely give you that. I barely give you that. Okay, but mostly left and right. And so if you cut the plane in 3 different locations, you see this very sharp onset. And note that at the highest masses above the Schechter mass, up to 90% of all galaxies show this. Very high duty cycle, very high duty cycle. So clearly, and independent of the redshift, we see an onset to a very high duty cycle nuclear outflow component. Now, these outflows are energetically much more important because, of course, they have, about 5-6 times the velocity, and square that times the energy of the star-forming wind. So this wind material, in fact, can go into the halo and can drive gas out of the galaxies. So the question now is, of course, have we shown any causation? Or have we just shown a correlation? And I would argue, well, okay, let's plot the same thing again. As a function of stellar mass, the AGN incidence and the AGN outflow incidence. Now, that's the blue and red points, which I've just shown you before. But let's also plot, inversely, the star formation rates, or specific star formation rates, and the gas fractions. And, they sort of do the same thing. The gas fractions go down, and the star formation rates go down exactly where the AGN outflow phenomenon goes up. So that's, I would say, a pretty close call for a direct consequence. Now, I've talked about the ionized gas, and that's what can be done right now. Of course, it begs the question whether what happens in the other phases. I raised that earlier. We will not be able to look at the hot phase, but we will be able to look at the molecular phase. And there is beginning to be evidence for this from molecular observations, broad components, in nearby star-forming galaxies here with ALMA from Bolato, from Herschel with OH absorptions, and now from ALMA in a number of cases. Here it's one of the very massive galaxies in our sample here, where you see extended and high-velocity molecular emission at the same time as you see ionized gas. So there is, at least on the mid-time scale, the hope that one will be beginning to sort of quantify a little bit the molecular outflow occurrence and maybe the rates, although there I'm a little more cautious because it's not easy to actually get from an intensity to a column density in this kind of regime, which is untested. So here's the summary. The outflows can be now studied in fairly robust samples of 600 galaxies across the entire redshift range and stellar mass star formation rate plane. We can distinguish between disk outflows as triggered by star formation and nuclear outflows. Once you have done this, you find that they behave totally differently. The stellar outflows know only about up and down and star formation surface density, whilst the AGN outflows know mostly only about stellar mass and size, actually, and 80% in the upper mass regime of all star-forming galaxies at high redshift have such an AGN outflow. Thank you.
To what extent can you tell whether some sources have both star formation outflows and AGN outflows?
Yeah. You do. I showed you one. Well, if we have adaptive optics data, we can, because then we can resolve the very extended stellar outflows as an extended component. In the seeing limited data, it's much more difficult. And I would say, indeed, you can see this if you go to the high mass end. We are losing star formation sources, which ought to be there just on the basis of the same kinds of fractions. So I'm with you. I think we do. And the AGN is the dominant one. So as soon as you have an AGN outflow, you hardly see the star formation outflow.
I have two questions, Reinhard. I'll give you the technical one first. The densities you're estimating from sulfur-2 of several hundred particles per cubic centimeter, that should give you an excited silicon-2 about 10%, even a bit more from the ground state, which should be easy to see in absorption. Are you seeing that in your spectra?
We don't have it. Our spectra would have the K-band, and your line must be shortward of this. So,
right, so there's plenty of Lyman break spectra out there. Do they see it?
This is on the list, but in fact, again, go back to a program committee and say, I have 600 objects for which I now would like to have a shorter band. And they will go back and say, well, wait a second, why didn't you? Yeah.
There's plenty of data published, so you can check that. The other one is, I guess I'm surprised in the incidence rate. We're told outflows are ubiquitous, and yet you're only saying 20 to 30% of your samples, so I'm missing something there.
Well, okay, our fields are Cosmos, UDF, and Good South. So in Good South, the fraction at the high mass end of X-ray detected sources is about 25, 28%, but not in Cosmos. Cosmos is much shallower, so it's 10% there. So it's a question of depth of the fields.
Could you tell us more about the decomposition of some of these emission lines that you did into the when you were fitting outflows?
Anna, the question is the technology of the fitting.
It's not easy to do. Are there? Yeah.
Anna, you have to speak up, please.
Okay, so you're not finding like potential degeneracies in the fits.
For the densities, yes, but I would say for the outflow velocity, you have seen it logic, and this is once you stack 20, 30 of these 8 hours.
All right, let's thank the speaker again.